Hi everyone, thank you for joining the SolidCAM Virtual Summit. My name is Anthony Calderone and I am the Chief Technical Officer at SolidCAM. In this presentation, we'll be going over the amazing secrets of iMachining 2D and 3D. So iMachining is made up of two modules. The first is the Intelligent Toolpath Generator, and the second is the Technology Wizard. So before we talk about the secrets of iMachining, let's talk about what iMachining does. So iMachining is about saving cycle time at the CNC. So here we'll go over a couple quick slides about some of the savings. So here we have iMachining 2D being used on aluminum for electronic products. And here you can see we have aluminum 6061, and this customer had 400 pieces to produce. Their standard machining time before iMachining was 17 minutes, and this decreased to 6 minutes. So this is a total savings of 65%, which leads to a total cycle time savings on the whole part run of 73 hours. Here's a really small titanium little bracket. This customer had 75 pieces to produce, and this part went from 17 minutes down to 3.5 minutes, which was a total savings of 80% per part, for a total time savings for the complete run of over 16 hours. We have a customer in Germany who uses a combination of iMachining 2D and 3D, which most of our customers are doing. And for them, in using aluminum parts, they're generally seeing savings of 65 to 75%. So I think what's nice to notice here is that iMachining is giving an amazing savings amount, whether you're doing soft materials such as aluminum or something very hard to machine such as titanium. Here's another part which is cut in steel, and this part went from 146 minutes down to 28 minutes for just this one single component. Now, besides the reduced cycle time of iMachining, there's another major factor on the CNC, which is reduced machine wear. So the iMachining Toolpath, and we're going to be reviewing this, it's a constant load toolpath throughout the entire cutting process. So what you'll notice when most of our customers are cutting with iMachining is you see spindle load ranges in the 4 to 17%, and it stays constant through the entire machining cycle. Hermle actually concluded that iMachining was the best toolpath with the constant force of all high-speed machining toolpaths. And Makino also tested iMachining on its machines and reached similar conclusions. And in the end, a constant load on the spindle is going to decrease your CNC wear and extend the life of your spindle. So why don't we watch a quick little video on iMachining 3D. And remember, iMachining 3D is using iMachining 2D, so we're seeing the same technology. So this is a steel part being cut with a 16mm end mill. And I know most people when watching this are thinking this is aluminum, but this is steel. And with iMachining 3D, this uses our step-up technology to bring the model to a net surface finish. Okay, so I think many people, when we watch these high-speed machining videos online, many people are questioning, well, that's great. In a single video, you can make something amazing show. But how does an everyday customer achieve this? And I think this is really where iMachining sets ourselves apart from every other CAM system out there, is that our customers are achieving those results day in and day out on every part they cut. And I'm going to go over the secrets of why this works and how this works. So the science behind iMachining. So the most important thing to note is that iMachining uses a variable cutting angle. So this means we work between a maximum range and a minimum range. And we also use a variable feed to keep the constant speed spindle load. Now we use variable feed to keep a constant chip thickness. Now, before we get into chip thickness, I have a small video I want to talk about and actually show. So this is a close-up video of not a helical end mill, but a turning insert. So that way we could get a very high magnification of what the cutting process is. So I'm going to press play and we're going to talk about this. So what we see here is the insert is being, drawn across the material. And what actually happens here is two things. One, we have what's called plastic deformation, which is at the tip of the cutter, you can see that the material, press play again, is going from a solid to kind of like a soft liquid here. And then you have shearing. So what for the material to actually break the bond, so that way you get a chip, you actually have to have this plastic deformation and then the material is shearing off. As you watch this cut, what's interesting to note is that you will sometimes see some of the chunks come back along the underside of the tool, and then that rubs against the back part of the relief. Now, when we talk about cutting and machining, a lot of times people are talking about getting underneath of the material, like pulling enough chip that the tool is actually cutting. And this is a very important thing to notice, because you could imagine here, if we weren't taking a big enough chip, this plasticized material right here would be constantly rolling around the bottom, and you would, instead of getting a nice shearing effect where 99% of the material is being drawn up the cutting edge, you'll start getting you're getting like maybe half of the material that will start, some will come up, some will go down, and this is a problem. And now when you do look at different tools for different materials, you'll see that this corner radius will change. Obviously with aluminum cutters, you have more of a knife edge here, and in aluminum you're really trying, they're able to cut more than having this brute force kind of shearing effect. But you can't use a very sharp edge in steel, because this plasticized material in steel will end up breaking down that cutting edge much quicker than it does obviously in aluminum. Let's go to our slide again. So we use a variable feed to keep that constant chip thickness. This was the plastic deformation and shearing that I went over. And then I have one other animation I want to show, which is now actually a helical end mill animation. And this is actually like a software generated animation, because we can't actually record a cross-sectional view of what a helical end mill looks like cutting. Oh, I want to open this with Windows Media Player. So the reason I open this up in Windows Media Player is I am going to go frame by frame. Now what this animation is depicting, and when the flute comes back around I'll show it. So this is depicting one revolution of a helical end mill. And so this is the x-axis. So basically the tool is moving along the x-axis, and as the tool is moving, it's also revolving, right, and it's cutting. So let's look at this process. What you can see here at the beginning of the cut is this is actually our chip thickness. So this is where that shearing is happening. So if we think about the previous video that we did, right here at this very tip, this is where we're getting that plastic deformation, and you now have material being in the form of a chip curling along the inside here, and as the cutter fully does its full revolution, that's what ends up with, one complete chip. And if we continue playing, you can see in this one revolution, the tool goes from this thick chip thickness to 0 chip thickness. So this is a very important thing to pay attention to, is that the tool is actually going from cutting its full thickness of material to 0 material at the very end. So you could imagine, when you think back to that plastic deformation video, the tool, when it's down here at the bottom, you're probably not really shearing off and getting a perfectly clean cut down here, because you're going to a 0 condition and you get it kind of rolling along the back side of the tool here, and it kind of, the material being plasticized, it's deforming and it can push a little bit. So this is quite an abusive process for the tool, and we'll play it. I'll play one more revolution. So as the next flute comes around, so we're going from the thickest part of the tool, or the thickest part of the chip, it's revolving, and then we go down to 0. And I'll just play a couple more revolutions. I'll zoom in a little bit here. And once it does one more revolution, you're actually going to be able to see a little bit of the scallop on the wall. So it's probably a little hard to see, but here you actually get the scallop, right? So this is the peak of the scallop and the peak of the scallop. So when we talk about like the surface finish, or the RA finish of the material, this is the height of this scallop. And one thing I think is kind of an interesting thing to mention is that there is the theoretical scallop or surface height. And this is in iMachining, you can actually select the surface finish that you want. But in reality, when the tool is cutting, as we saw from that plastic deformation video, you don't get the perfect scallop like you think here. So this portion here, this peak, is probably almost always going to be a little bit higher in real life than what the theoretical perfect scallop would be. Now we'll go back to our presentation from the current slide. So we talked about the helical end mill, so let's talk a couple things about climb, conventional, and full slot cutting. If we were to take that helical end mill and we were to do a full slot cut, which is depicted here on the left, you can see that the tool would actually be going from the thinnest part of the chip, reaching to the thickest part at 90 degrees, and then coming back down to the thinnest part. Now you can imagine, if you're cutting something like aluminum and you have a very sharp cutting edge, it might be okay if when you're starting down here at the thinnest part of the chip, but it's still not good for the tool, because it needs to deform that chip right there at the cutting edge, and it needs to plasticize it enough that it can shear it off. So anytime you're starting with conventional cutting like this, you're not getting cutting right away, and that's bad. So if we think about this, I mean, realistically, when you're doing conventional cutting, the tool is probably not really pulling a chip until it reaches about here, or maybe like here in the cut. So that whole time, the tool is really just jamming itself, and what you're probably getting more than a chip being formed, you're getting that glob of material that's actually rubbing along the back side of the flute on the relief, which is really bad. Now, iMachining is also only doing climb cutting, and this is important for the force of the tool. So if you were to take like an indicator and just put it on the tip of a cutter, and then just like push on the cutter a little bit, you'll actually see that the indicator will move. This is because there's flex in the whole tool spindle assembly in the machine. So one of the things we don't want to have happen in the CNC is we don't want to have the forces oscillating very much. So when we think here about the tool, let's say we're always cutting from like 90 degrees down. You're always getting that the force on the cutter is always in this range, and it's always pushing that way against the tool. If you're doing full slot cutting, you're getting the cutting force coming down this way, and then at the very end, you're getting the force coming up this way. So you're actually getting like negative or opposing forces from the beginning of the cut and the end of the cut. So you're getting pressure this way at the beginning, the tool is revolving, it's coming this way at 90 degrees, and then down at the bottom, it's coming this way again. And that is not good for the spindle, and it's not good for the tool, because there is flex. You cannot get rid of the flex in the tool holder assembly. So we don't want that flex, and we want to try to limit it. So iMachining is limiting itself to this 80-degree range, so that way we're always climb cutting and keeping that cutting direction in the same way, so the tool is always flexing in just that one way. Chip thickness and chip load, and are they the same? So as we know, if we open up a machinist handbook, everything is going to be about chip load. And chip load is what refers to the amount of chip at 90 degrees. So this is our thickest part of our chip. Chip load and chip thickness are the same value at 90 degrees. When we are actually cutting not at 90 degrees, the chip thickness is not matching chip load anymore. So let's say we had the same chip load and we're trying to run a chip load of 4 thou. When you are cutting less, let's say 40 degrees, the chip thickness is actually not 4 thou. So what does that mean? That means the tool, let's say for that material on that tool, it wants to reach a 4,000th chip load or chip thickness where the tool will properly shear away the material from it and form a nice chip. Well, if you're going less than 90 degrees, your chip thickness is actually smaller. And if we come all the way down to like 10 degrees, here's this little graph. You can see the original chip load is here. This chip thickness is very tiny if you don't increase the feed rate. So what iMachining does is we actually adjust the feed rate so we have a constant chip thickness. So if this tool wants to have a chip thickness of a certain distance, we need to maintain that. And if we look at 80 degrees, you can see that 80 degrees is pretty close, but even at 80 degrees, you need to adjust chip load to have a constant chip thickness. Another important part of adjusting for or getting a constant chip thickness through the cut is feed of the center of the tool versus the edge of the tool. So if we think about like runners on a racetrack, the runner on the inside track, he is always staggered further behind everybody else because technically he has the shortest linear distance around the track. So the same thing is happening with an end mill because the CNC is controlling the feed rate at the center of the tool. But the reality is the cutting is happening at the edge of the tool. So what iMachining, what we do is we adjust feed rates on arcs or linear segments that represent arcs. So this means on internal corners, we are actually slowing the feed rate down so that way we can get a constant chip thickness. So if we don't correct the feed for an internal corner, you can see that FZ, this is the chip thickness out here at the edge of the cutter, it's huge. Like we want this FZ right here along the straight wall. You can see up here it's about like 2 to 2.5 times larger. Now when we correct the feed rate and slow down for internal corners, now the same chip thickness that we have on the straight part, on a straight line, is the same that we're getting on an arc. So what is an iMachining toolpath and what does it look like? So a couple things, main things you're going to note with iMachining. One, we have controlled step overs. So you're never going to see any overloading of the tool, and this is a lot of the engagement angle stuff that we were talking about. You're also going to notice that there's exact stock machining. This means there's no air cutting, and this is important because we manage how much of the tool is actually engaged with the stock at every part of the cutting. And then we have smooth tangent toolpaths. Obviously, if we want to control the load to be the smoothest on the tool, we need to not have abrupt direction changes, and you should see something smooth and tangent the entire time. So here's a part with several pockets in it. And generally what you're going to notice with iMachining is you're going to see, if it's a closed pocket, you're going to see a helical entry into the center of the pocket. You're going to see a morphing spiral from that circle out to whatever the shape of the pocket is. And then you're going to see parallel passes to clear out the rest of the pocket. And this general process you're going to see no matter what the geometry is. Now here we have an example of a pocket with some islands. Now generally a lot of our customers, we don't see many pockets that have islands in it. It seems like electrical housings like this one are parts that generally have multiple islands, or at least more than one island in it. But this is a nice example to show the process of what we do. So first we have a morphing spiral. So you can see the helical entry, we pre-drilled out the hole so we didn't see the helical entry. It plunges down into the hole. And this starts from a circle, and then look at the shape it morphs out. You can see more dense toolpath down here and a higher toolpath up here. So this is one continuous pass to do this entire area. When we hit the islands, we have what we call separating islands or separating channels, and these go around the islands, and after the islands are done, we are now able to go back to morphing spirals. And once again, with the morphing spirals, you can see down here in this area, you have a denser toolpath, and along the other areas, you have a thicker toolpath. Then we run into an island again, so then we make a moat, moat or an island around it, and then we go back to our morphing spiral. So that's the basis of what you see with the iMachining toolpath. Now, what do we do when we run into iMachining 3D? So as you saw from iMachining 3D, we do Scallop Step-Up. And what is Scallop Step-Up? What this does is we give a constant net surface finish across the entire model. And so all the user has to do is say what scallop he wants, which is the distance from the final target model. And then iMachining automatically calculates different step downs and step ups to achieve that. So over here on the left-hand side, we have just a cross-section of a very simple tapered pocket. So as we see on the less steep area, we have 7 or 8 passes. On the steeper area, we only needed 4 passes. Both of these give the same scallop height. This makes the toolpath extremely optimized, and it makes the toolpath not do excess cutting, as opposed to what a lot of people have to do is just pick the smallest step down possible, and then you just get a lot of redundant cutting that you don't need, and that prematurely wears out the tool, besides it being a much longer cycle time. iMachining 3D also has minimal repositioning. So you can see, like in these pockets, this is just rest machining. The tool is able to stay down through all the machining. This minimal repositioning is a huge time savings at the CNC. And I think everybody is used to seeing in the CNC, every time the machine does rapid moves going from one spot to another spot, it can be some of the slowest times in the machine because the thing's just coming from this area, bouncing over, coming over here. And in 3D, this happens a real lot because you have a complex model, so it's cutting over here, it's cutting over there, and it goes around to the different areas. We also have exact air cutting, as I said before, so this is whether it's iMachining 2D or iMachining 3D. We are only cutting areas where there's material. I mean, this is just a beautiful example of just cleaning out this corner. And over here on the right-hand side, you can see our solid verification, and the purple color is just showing the area where the rest machining is accounting for. Now, besides just the toolpath side, we now have a problem with feeds and speeds, and this is the second part of our module we talk about. When we're doing the machining process, we have the material, the tool, the geometry, and the machine. So what does this mean? This means for the material, us as programmers, we need to take into concern the cutting speed, the hardness of the material, min and max step overs. For the tool, we need to know the length of cut, number of flutes, helix angles, chip thickness, hardness. For the geometry, we need to know the depth of cut. For the machine, we need to know the spindle speed, the maximum feed rates, the maximum horsepower, the memory size of the machine. And these are all variables that we, as a programmer, have to manage. The solution here is the iMachining Technology Wizard. What the iMachining Technology Wizard is, it takes out all the guesswork out of all of that. And what it does is it takes in machine material geometry and tool. And the final result of it is it gives you a condition of feed rate, step over, spindle speeds, and depth. And most important is it synchronizes all of this for you. So whenever anything changes that needs to be adjusted, the iMachining Wizard handles all of it together. For instance, you might just have to be able to adjust for the maximum RPM of the machine. Well, at some point, if you try to run your machine at, let's say, 16,000 RPMs all the time, your feed rate might actually be too fast for you to hold the chip thickness that this toolpath is requiring. So you actually have to have a lower spindle speed to hit the chip thickness that you need. The iMachining Technology Wizard is taking care of all of this for us. The iMachining Wizard also has our slider. And what does this mean? This slider is here because iMachining is not able to understand 100% of the process of what's happening at the CNC. This is why we still need a CNC programmer who is using his intelligence to understand the fixturing, the tooling. Is it a really long extended tool? What type of vibration problems are you having? So the iMachining slider gives you the ability to go from the lowest level to the highest level and with interpolated steps. Most of our customers are able to go right to level 6 and have great success cutting right out of the box. But if you know you have like extra vibration or you have like a weak fixturing, you can lower the machining level down, or you can bring it up if you know you got a nice stubby tool and you got a really good fixturing. Another part of why iMachining works so well is helical endmills have something that we call axial contact points. And the way I like to describe axial contact points is with an actual shell mill doing facing. So let's say you have like a 4-flute shell mill. When the tool first enters the material, we hear the dunk, dunk, dunk of each insert hitting the material. And then once you get 180 degrees of the face mill actually fully in the material, you hear it quiet up, right? So you hear the dunk, 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 dunk at the beginning, and then it goes, and then you just hear that constant sound. And then at the very end, when the tool breaks out of the material, you hear that dunk, dunk, dunk again. And when we look at the surface finish of a face mill, you always can see the beginning of the cut when the tool is trying to enter. Then you see the cut along the entire geometry, and then you see the end result. This is because you have multiple teeth in contact or multiple inserts in contact with the material, and that gives a stability to it. The same thing is happening with helical end mills. You can cut with only, if you have less than 1 flute in contact with the material, you know what you're going to have? Vibration. You're going to get the helical, every time the tool revolves, you have the tool loading and unloading entirely. So it's going dunk, 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 for however many RPMs you're doing, times the number of flutes. When you do deep depth of cuts, you get multiple axial contact points. This puts multiple teeth in contact with the material, and you get silent cutting. There's no vibration. And in iMachining, we give feedback on that. So those are some of the secrets of why iMachining works. This was not meant to be a presentation on using iMachining in SolidCAM. I'm really excited to be able to talk about the technical aspects of iMachining because this is really what separates us from our competitors. We care about the machining, and we care about all the load and the cutting that is happening at the CNC. A lot of the things that I talked about here in this presentation are the same things that Ken talked about in his interview. This I tried to give kind of a graphical depiction of what was going on, and I hope everybody really understands that not using iMachining in your machine shop is really a disservice, and it is the single biggest thing you can do to decrease your cycle time and get more machining capacity. And I will end off the presentation with The best quote I think I ever hear is from Greg Burns.
My hopes is that not too many people learn about iMachining because it is my biggest competitive edge.
I think Greg says it perfectly, and it is the truth. So thank you very much for listening to my presentation. I hope everybody has a great time at the virtual summit. And for any of you that are not cutting with iMachining, please, please, please call your reseller and ask for a trial version of iMachining. It truly is a life-changing experience, and we look forward to hearing the awesome words that you can say about iMachining. Thank you very much.